Alrighty, howdy folks. So let's jump to chapter 6, section 4. The previous section I had covered was something in chapter 5. I believe it's chapter 5, section 5. But I jumped to chapter 6, section 4. Why is that? That's because the previous section was about inverse trigonometric functions and their graphs. But now let's apply these inverse trigonometric functions to specifically right triangles. So to me, that is a natural transition. So let's do that. And the first problem itself is find the exact value in each of the following cases. And the first thing is sine inverse of 1 equals what? Okay, two questions should pop up in our head. Can you actually find sine inverse of 1? And that's dependent on, is 1 within the domain of sine inverse, that is negative 1 to 1? Yes, 1 is in negative 1 to 1 interval, so we can find sine inverse of 1. The second question is, if so, sine of what angle equals 1? And of course there are infinite answers to it, but you should force yourself to ask sine of what angle between negative pi half to pi half is equal to 1. Sine of what angle between negative pi half to pi half is equal to 1? Well, the answer is sine of pi halves is 1. Is pi half within negative pi half to pi half? Yes, it is. So sine inverse of 1, ladies and gentlemen, is pi half. As simple as that. Cool? All right. Cosine inverse of 0. Once again, can you find cosine inverse of 0? Is 0 in the domain of cosine inverse? Yes, any value between negative 1 to 1, including negative 1 and 1, we can find cosine inverse. And now the question is, cosine of what angle equals 0? Cosine of what angle between between 0 and pi, is equal to 0. So cosine of pi halves is 0. So cosine inverse of 0 happens to be pi halves. Cool? All right, another problem. Tan inverse of square root of 3. Can you find tan inverse of square root of 3? Oh, tan inverse, the domain is all real numbers. So tan inverse can be found of any real number. So square root of 3 is not an issue at all. So the only question is tangent of what angle between negative pi half and pi half is equal to square root of 3? To me, when I think about this, it's like, so somewhere sine is square root of 3 over 2 and cosine is 1/2. Where is sine equal to 3 square root of 3 over 2? At 60 degrees or pi third radian. So pi third radian is the answer. Fairly quickly we can find that, okay? Problem, sine inverse of negative square root of 2 over 2. Is negative square root of 2 over 2 between negative 1 and positive 1? Yes, it is. Sine of what angle between negative pi half and pi half is negative square root of 2 over 2? The answer is negative pi over 4. Okay? And cosine inverse of negative square root of 2 over 2? See, this is an interesting one. It is true that it is not true that cosine of negative pi fourths is negative square root of 2 over 2. Cosine of negative pi fourths happens to be the same as positive cosine of pi fourths, right? And that's actually square root of 2 over 2. Why do I say that? Because negative pi over 4 is in the fourth quadrant and cosine of a fourth quadrant angle is positive. So where do we go for negative square root of 2 over 2? Oh, we go to the second quadrant. So this angle must be somewhere in the second quadrant. Okay, second quadrant, sure enough, cosine is negative. So that's why I'm saying that cosine inverse of negative square root of 2 over 2 must be in the second quadrant. Cool. What angle? Use the reference angle. 180 minus 45 must be the answer. That means pi minus pi fourths must be the answer, which is 3 pi over 4. Cool? So that's how I would find cosine inverse of negative square root of 2 over 2. What's up with tan inverse of negative square root of 3? Well, we can find tan inverse of any real number, so negative square root of 3 shouldn't pose a problem. And the only question is, do we know the exact value? The exact value means we need to look at an angle in the fourth quadrant, right? In fourth quadrant, tan inverse of tangent of what fourth quadrant angle equals negative square root of 3? The answer is negative pi thirds, right? That's it. Let's move on. Find the exact value. Cosine of sine inverse of 4/5. That's an interesting one. Notice how we are not saying, had we said sine of sine inverse of 4/5, then the answer would have been 4/5, end of the story. What? Because you recall the property of inverse functions, f of f inverse of x is equal to x, provided x is in the domain. Right, so cosine of a sine of sine inverse of 4/5, there wouldn't have been a whole lot of work. We can simply say that's 4/5. But now we are being asked to find cosine of sine inverse of 4/5. How do you do that? That you need to say, let sine inverse of 4/5 be equal to theta. Okay, let sine inverse of 4/5 be equal to theta. And then that theta better be in negative pi half, in the interval negative pi half to pi half. In other words, that theta better be in the fourth quadrant or the first quadrant, right? That's a fancy way of saying this theta is in negative pi half to pi half is a fancy way of saying fourth or the first quadrant, because negative pi half to 0 would be fourth quadrant, 0 to pi half would be the first quadrant. Okay, that is theta in either quadrant 4 or quadrant 1. But then, since the argument of arcsine is positive, theta is in Q1. What in the world do I mean by that? I mean, look at the argument of sine inverse here, or arcsine. It is positive 4/5, right? So that means sine of theta must be a positive 4/5. If theta were to be in quadrant 4, would sine theta be a positive 4/5? No, because sine theta is negative in quadrant 4. That's why, looking at the argument positive 4/5, we can say that theta must be in Q1, the first quadrant. It has only two possibilities, fourth or the first, but because it cannot be in fourth, it must be the case that it is in the first quadrant, and sure enough, sine of an angle in first quadrant is positive. You see that? Okay, based on that, further, sine inverse of 4/5 equals theta implies sine theta must be 4/5. That's the very definition of a sine inverse function. F inverse of x is equal to y if and only if f of y equals x concept. When we say sine inverse of 4/5 equals theta, we can confidently say that sine theta must be 4/5, and that's what I did. And once again, I'm recalling as to what is sine theta in terms of opposite hypotenuse adjacent is opposite over hypotenuse, but in terms of x, y, and r is y over r, and we know theta is in Q1, so I'm ready to draw the picture. Right? Literally, that old Chinese saying about a picture is worth 1,000 words is most certainly true in a case like this. So knowing that sine theta, which is y over r, is 4/5, and theta is in the first quadrant, let's draw the picture. So we show theta. Clearly, y happens to be 4, and r happens to be 5. And using the Pythagoras theorem, we'll figure out what the other leg ought to be, which is hypotenuse square minus the leg square all over, all under a square root. So this is 3. Cool. So now that we have every angle, every length of this triangle, we are ready to figure out whatever we need. For example, here apparently we need cosine of a sine inverse of 4/5. Any idea how we are ready to figure out cosine of sine inverse of 4/5? Didn't we say sine inverse of 4/5 is theta? So could I replace sine inverse of 4/5 with a simple theta? Yeah, I can. So what does this become? Cosine theta. But cosine theta is x over r. Right? What is x? 3. What is r? 5. So this is 3/5. Done. Right? What if the question had said, okay, same situation. What is tangent of sine inverse of 4/5? Right? We would say, oh, wait a minute. Tangent of sine inverse of 4/5 would be tangent of theta. Tangent of theta is y over x. So that means 4 over 3. And we would be done. You see the whole idea? You must know how to solve these problems. Okay? I'll do quite a few more. Tangent of cosine inverse of negative 7 over 25. The process is still the same. We say let cosine inverse of negative 7 over 25 be theta, and we know that theta must be in 0 to pi, right? Okay, now 0 to pi would mean what quadrants? First or second quadrants, right? So theta is in either quadrant 1 or 2. Well, now let's look at the argument of cosine inverse. That's a negative value. So which quadrant it must be? Is any ratio ever negative in the first quadrant? No. But in second quadrant, could cosine be negative? Yeah, cosine is in fact negative. So this means we actually have the theta in quadrant 2. Cool. And further, cosine inverse of negative 7 over 25 is theta implies cosine theta itself must be negative 7 over 25, which actually is x over r. So what do? We'll draw once again our figure. This time we'll show the angle theta in the second quadrant and immediately identify x to be negative 7 and r to be 25. And then use the Pythagoras theorem to say this must be 25 square minus negative 7, the quantity square. That's the leg, right? Is 24. So based on that, now if we need to find tangent of cosine inverse, we can replace cosine inverse of negative 7 over 25 with a simple theta. So this is equal to tangent of theta, and tangent theta is equal to x over y. X is negative 7, y is 24, and so that's negative 7/24. And also let's ask, does it make sense that tangent theta in this case turned out to be a negative value? Yeah, since theta is in the second quadrant, tangent must be negative. Only sine and its reciprocal cosecant are positive in the second quadrant. So we can feel somewhat confident about tangent theta being a negative quantity here. Cool. Next. Secant of tan inverse of negative 5/12. Well, the process is similar. Again, let tan inverse of negative 5 over 12 be equal to theta, but theta must be in negative pi half to pi half because we are looking at tan inverse, and that is quadrant 4 or 1. Since the argument is negative, theta must be in fourth quadrant, and so we'll say tan inverse of negative 5 over 12 is theta. That implies tangent theta is negative 5 over 12. That's equal to x over y. Am I flying through these things? Yes, but my hope is we have gone through similar problems quite a bit, right? For the sake of completeness, I'm trying to solve a whole bunch of problems and show you this is in fourth quadrant, so let's draw the angle in the fourth quadrant. And am I right in showing this way? Perhaps, yeah, no, I'm okay. We do have, we will come up with a negative angle. So yeah, that's right. X is positive. Wait, did I goof here? When we have x over y to be negative 5 over 12, shouldn't I have said x equals negative 5 and y is positive 12? Oh no, I shouldn't. What I did is actually correct. Because negative 5 over 12 could actually be 5 over negative 12. In fact, that is the case over here, because notice the x value must be positive, whereas the y value must be negative for something in fourth quadrant. So I made sure that I was correct in calling this as positive 5 and this as negative 12. Okay, so we have 5 and negative 12, and Pythagoras theorem tells us the hypotenuse must be 3, or r must be 3. I shouldn't say hypotenuse in this case. R must be 3, must be 13 rather. Okay, and then the rest is simple. Thus we have secant of tan inverse of negative 5/12 is secant of theta. Secant of theta is the reciprocal of cosine, so instead of x over r we have r over x, and that's going to be 13 over x is 5, right? Okay, give me just a second. All right, I'm back. Sorry about that. Yeah, this thus we have secant of this is r over x is 13 over 5. That's where we left off. Again, as a quick check, we can see, hey, secant of theta turned out to be 13, positive 13 over 5. Does that make sense? Yeah, theta is in the fourth quadrant where cosine and its reciprocal secant are positive, so our getting a positive value actually makes perfect sense. All right, okay, a few more problems. A satellite flies at a height of h from the surface of the earth whose radius r is roughly 3,960 miles, about 4,000 miles. Here, the arc length s indicates the farthest distance of two objects on the Earth that the satellite can see. So let's take a look at this. So satellite is positioned way up here, and it can see this horizon, right? Which is nothing but a tangent to this circle. Sphere in one view will look like a circle. So this is actually a sphere. Hey, I got news. Earth is actually a sphere. You know what the joke is? Apparently there are some people who think Earth is flat. Flat earthers, they are called. That's a bunch of nonsense. Anyway, so Earth is a sphere. So in one view, it actually looks like a circle. You can approximate that to be a circle. And so this line is actually tangential to that Earth. Similarly, this is tangential to that circle. All right. And so if it is at a certain height, it can see this much of area. Whereas if it is higher, it can see a larger amount of area. But no matter how high you go, you will never see the whole Earth. You can only see 1/2 of the Earth, right? Okay, and something else. If you look at this arc length, that whole thing is S. What's the significance of this arc length S? Well, the significance is if there is one city, say over here, it can see, the satellite can see that city, especially if it is night and the lights are on. It can see the lights of one city, and all the way on the other side, it can see the lights of another city. flying at this distance. So if we measure this arc length, we have actually found the farthest distance that the satellite can see flying at a certain height. What is that height? Notice that EDB from the surface of the Earth to where the satellite is, that is h. H is not all the way from the satellite to the center of the Earth. No, it is not. It is only the height from the surface of the Earth to the satellite. And what they have done here is they have just extended that line so that it meets the center of the Earth, and they drew two other dotted lines indicating these are this is the radius of the Earth, and so is this. And please pay attention to this. Did I mention that this line is actually tangential to the circle? Yes. So what's the implication of that? The implication of that is this must be therefore a right angle. Similarly, this must be a right angle. Cool? So that is very useful information for us to be able to answer some of the questions here. Express the angle theta as a function of h. Express this angle theta as a function of this height. As the satellite flies at a higher height, the distance h increases, then what happens to theta? We should be able to talk about those kinds of things. So let's try to find out a formula for theta as a function of h. Similarly, express the distance s as a function of theta, right? Third, express the distance s as a function of h. To me, that is a more useful version. So what is it basically saying? Hey, if I fly at a certain height, what's the maximum distance I can see? Two cities, at what maximum distance can I see if I'm flying at a certain height? Right? That's a very useful one. And in fact, they actually ask us to find some for specific cases. If the satellite is 100 miles above the Earth, what's the distance s that it can see? Right? 100 miles above the surface of the Earth. And then they say, how high does the satellite have to be to see both Los Angeles and New York 2450 miles apart? Right? Okay. A confession. I like this problem a lot. I like it because, believe it or not, I got curious about precisely this one day when I was flying to India. I recalled that my mom comes from a city which is about 90 miles from where I grew up. And most summers we would go to my mom's city and spend some time. And they are exactly 90 miles apart. I don't know about exactly, let me rephrase that. They are 90 miles apart. And as I was flying, I would look down and I would see two cities and wonder, how far are they? And then I would recall, those two cities, my mom's city and where I grew, they are 90 miles apart. Flying at this height, typically it's 32,000 feet, 30,000 feet or something like that. Flying at this height, would I be able to see both the cities? And then I said, wait a minute. I can figure that out. I'm an engineer and I know the math that I might need to use. And so I asked the flight attendant if I could borrow a piece of paper and some writing stuff. And so she had a piece of paper and gave me a pencil. I sat down and I drew a figure just like this. And I knew Earth was about 4,000 miles. And I figured all of this out. And I wrote it nicely. And then I called the flight attendant and said, Miss, could you please do me a favor? She said, let me see. Okay, these are the calculations I did. And based on this, flying at 32,000 feet, I think the number came to about 200 miles or 300 miles, something like that. I can't remember that number. This claims, my calculations tell me that one should be able to see two cities that are 300 miles apart. Okay, am I being at least, is this calculation even reasonable? Could you please ask the pilot if my calculation is reasonable? And she thought that was such an unusual request, chalked me up to being some kind of a nerd. And sure enough, the nice woman she was, she actually went to the captain, and after about 20 minutes or so, she came back. Not only she, but the captain himself came. And he said, that is a very interesting calculation. That seems to be about right, because I tell you, there was a time when I was flying, and in the night, I could see three cities: Philadelphia, New York City, and Boston at the same time. Like one, in my field of vision, I could cover all the three cities. So your calculations probably are right. Man, I felt great about that. So I thought I'll share that with you. Cool. All right. How do we do this problem? So what I've done is I've just isolated this triangle. Okay, that whole right triangle. First things first, is that dimension just the radius of the earth r? So that's why I said that's r. Again, is that angle 90 degrees? Yes, because this line is tangential to the circle. That must be 90, and that's why I have shown a 90-degree angle here. And this is, of course, theta. And the only question is, am I right in saying that this whole distance is h plus r? Yeah, because notice, this dotted line must be again r. This dotted line is of length r, this dotted line is of length r, this also is of length r. So r plus h should be the whole length. That's what I have shown. So if we know that, we are pretty much in business. Okay, A, what is that? Theta is a function of h. Cosine theta, looking at this, must be adjacent over hypotenuse or over r plus h, right? H plus r or r plus h. But r itself, we know the radius of the earth is 3960. So I plugged 3960 for r. So if cosine theta is that much, theta must be cosine inverse of that quantity, that ratio. That's it. Part A is done. Theta as a function of h. Now express distance s as a function of theta. That's an interesting one. So let's look at this figure. What is s? S is this total arc length. To find the arc length, do you remember the formula? S equals r times theta, right? But we got to be a tad careful here though. Theta is only talking about half of this arc length. We have a similar half on the other side as well. So S equals the radius times theta gives us only half of this one. And if we double it, we got the total S, right? So that's exactly what I'm doing here. S is equal to 2 times r theta, and r happens to be 3960. If we plug that in, we get 7920 theta, but theta obviously must be measured in radian. So we know the maximum distance in terms of angle theta is 7920 theta if the satellite is flying at a height of h. Okay, all right. Now what's the third one? Express the distance as s as a function of h. So here in part B, we have s as a function of theta. You agree? S as a function of theta. But in part A, we have theta as a function of h. So if we replace theta with this expression, we got s as a function of h. That's all I did. S is 7920 theta, and then I replace theta with a cosine inverse of 3960 over 3960 plus h. And so we got s as a function of h, just as this wants us to. Simple? Okay. Now part D. If the satellite is 100 miles above the Earth, what's the distance s that it can see? Oh, would you agree? Simple plug and chuck. The plug and chug, check, plug. Yeah, just, what's that phrase? Plug and check. Anyway, so let's just replace this h with a 100 and figure out s based on that. H is 100 miles, and so that implies s must be 7920 cosine inverse 3960 over 3960 plus 100. Replace the h with a 100. For this, of course, you have to use a calculator. I think I used MATLAB, punched this into MATLAB, and it said that's 1761.5 miles. Dang, isn't that nice? Right, 1761 miles apart. If there are two cities that far away, the satellite can still see both of them. Wow, mind-boggling. Perhaps it wouldn't be a bad idea to just open up Google Maps or something like that and look at two different places in the world that you know of that are about 1761 miles, close to 1800 miles, and say, wow, so you mean to tell me that the satellite can see both Sydney, Australia, and I don't know, Adelaide, or probably not Perth. Perth would be too far away. Well, so something like that. Fascinating. Finally, E. How high does the satellite have to be to see both Los Angeles and New York 2450 miles apart? So we can go to this problem, this formula in C, part C, and use that. The only thing is we know S to be 2450. What we do not know is H. So we solve 2450 equals 7920 cosine inverse of the unknown value H here. So it's just a matter of arithmetic, right? Or algebra. Divide both sides by 7920. You get cosine inverse of this. Now that means cosine of this quantity must be 3960 over 3960 plus h. Okay. And notice our objective is to find h. So let's cross multiply these two and divide by the cosine, and that should give us 3960 plus h is equal to this 3960 divided by the cosine. And now to find h itself, subtract 3960 from both sides. So what I did is when I subtracted 3960, I observed that there's a 3960 on the numerator here and minus 3960. So I factored out a 3960 and wrote this as 1 over this minus that. If you don't believe me, just distribute and see that's exactly what it is. Would you agree this when we distribute, you have 3960 over cosine of this thing minus 3960? Cool. Again, I punched into calculator and figured out that this is 197.33, about 200 miles. So if the satellite were to be flying at a height of about 200 miles from the surface of the Earth, it would be able to see both Los Angeles and New York, which are 2,450 miles apart. Isn't that fascinating? I like it. Alrighty, that's it.